This video is a continuation of Chapter 13, Fundamental Equilibrium Concepts. In this video, we will continue with Section 13.4 by solving Problem 4 from the lecture handouts. Question 4 states, at a certain temperature, the equilibrium constant is 1.1 times 10 to the third for the reaction of iron 3 ions plus thiocyanate ions makes the complex iron thiocyanate. What are the equilibrium concentrations of all species if 0.020 moles of iron 3 nitrate are added to 1 liter of 0.1 molar KSCN? Again, we'll start by writing the balanced chemical equation. And the corresponding equilibrium constant. And then we'll go ahead and set up our ice table. So what is the initial concentration of Fe3+? Concentration is moles over volume, and it says we're adding 0.02 moles of FeNO3 in 1 liter, and there is 1 mole of Fe3+ per mole of iron 3 nitrate. This means there's going to be 0.02 molar of the Fe3+. We're adding it to 0.1 molar potassium thiocyanate. Since thiocyanate and potassium are in a 1-to-1 ratio, that's also 0.1 molar for the thiocyanate. And again, we'll assume 0 for the product. In terms of the change row, we're going to be proceeding in the forward direction. So we have minus X for iron 3+, minus X for the thiocyanate, and plus X for the iron thiocyanate. Our equilibrium row is the combination of the initial and change rows. And we'll plug these equilibrium values into our Kc expression. And our K value was 1.1 times 10 to the third. We see that we're going to end up with a squared term for X here. So we could use the quadratic formula to solve this. However, there's a simpler way. Notice that our value of K is large. What does that mean in terms of this reaction? That means at equilibrium, we expect mostly products. So in the expressions that we've written above, X is not expected to be small. So we can't do what we did in problem 3 and just neglect the X in these terms. However, we have another trick up our sleeves. I'm going to go to a new slide so we can look at this again. So we have our original equation, and our original ice table. Now, we're starting with all reactants and no product, so we just discussed how we don't expect X to be small in this case because we expect mostly products at the equilibrium position. So let's go ahead and push the reaction all the way to products. So I call this doing a stoichiometry step. Why would we want to do this? What we're trying to do is get the system to be close to the equilibrium position so that any adjustments that we make to get to equilibrium are small. So let's add a stoichiometry step, S. We're going to go from our change or equilibrium position here, and what we're going to do is push the reaction as far as we can to products. If we look at the two reactants, iron 3 plus and thiocyanate, which one is going to be the limiting reactant? Well, our iron is present in a smaller amount, so that's going to be our limiting reactant. If we push this all the way to the right, that's going to give an X value of 0.02, so that our new iron 3 plus concentration is 0. Our new thiocyanate concentration is 0.08, and we're showing 0.02 molar for product. Now again, this is not an equilibrium situation because we have 0 for one of our reactants. So we're going to add a new change row to shift us to equilibrium. In this case, if we were to evaluate Q, we would see that we would need to shift the reaction back towards reactants. So in this change row, we're going to have a minus term for the product. I'm going to call it Y this time to distinguish from our previous table. So the product will lose Y, and each of the reactants will now be gaining Y. Again, they all had a 1-to-1 ratio in the balanced chemical equation. So we have a new equilibrium equation. We have Y as our value for the iron 3 plus, 0.08 plus Y for the thiocyanate ion, and 0.02 minus Y for the product iron thiocyanate. We can put these expressions into our Kc value, products over reactants, and now we can probably make the assumption that Y is going to be small. Because we've shifted the reaction all the way towards products, at least as much as we could, any shift back should be a small amount. So we'll again neglect any terms, any Y terms in sums and differences, and get a new equation to solve that's much easier. Our K value is equal to 0.020 over 0.08 Y. Solving this for Y gives 2.3 times 10 to the minus 4. Now we of course need to check our assumption. What we want to compare is the value of Y actually small relative to both 0.08 and 0.02? We can actually just choose to check it relative to the smaller of the two situations. So our check, I'm going to put it up here, is to see whether 2.3 times 10 to the minus 4, our value of Y, is small relative to 0.02. And again, we'll express that as a percentage. And when we calculate that out, we get about 1%. Since 1% is less than 5%, we consider this to be a good value for our value of Y. Again, let me switch to a new slide so we can clean this up a little bit. We have now solved for our value of y of 2.3 times 10 to the minus 4. And we need to go back and plug that into our equilibrium expressions to get the equilibrium concentration of iron 3 plus, which was y in this case. Our equilibrium concentration of thiocyanate was 0.08 plus y, which approximately equals 0.08, as long as we are only going to the hundredths place. And our equilibrium concentration of iron thiocyanate was 0.02 minus y, which again, to the number of significant figures we're allowed, is just 0.02. So here we took a problem that would have required us to use the quadratic equation, but by making some assumptions and using some smart chemistry, we were able to simplify the math.